creo que puedo hablar directamente sin el... Ok, voy a hablar por acá para que me escuchen en la red. Bueno, hoy lo tenemos con nosotros a Igor Stanković, que viene de Belgrado. Él está participando del proyecto Ultimate, del cual también estamos participando nosotros. You understand me, Igor, ¿no? Ok. Él va a dar la charla en inglés, porque se maneja mejor en ese idioma, pero entiende español, de modo que tranquilamente le pueden hacer las preguntas probablemente en español, y si no las entiende tendrán que hacerlas en inglés. Bien, Igor va a hablar, creo que lo tengo por acá, perdonen, pero estoy con mi padre enfermo y entonces estoy pensando en otra cosa.
De pequeñas moléculas sobre las superficies de carbón.
Ok. Bien, Igor, como les dije, viene de la Universidad de Belgrado. Investiga en el Laboratorio de Computación Científica del Centro para Estudios de Sistemas Complejos, pertenecientes al Instituto de Física de Belgrado, en Serbia. Su trabajo se enfoca en las correlaciones entre la estructura y las características de transporte de gases, líquidos y sólidos. Utiliza la física estadística para establecer conexiones entre las propiedades macroscópicas de la materia y las propiedades microscópicas de sus constituyentes. Los campos de investigación de su interés son el transporte en medios porosos, el modelado multiescala, la fricción seca en metales y las aleaciones mecánicas. Los métodos de trabajo que utiliza son las siguientes: simulaciones mediante dinámica molecular, teoría cinética, termodinámica irreversible y soluciones analíticas y numéricas. Así que, bueno, I leave you with the audience.
Thank you very much for this introduction. So I come from Institute of Physics in Belgrade. So it is part of University of Belgrade, and we are about 250 researchers. And I participate in this ultimate project, which is funded by European Union. We have to say that, otherwise we get problems. And on this project, I'm participating as a part of the company, which is a spin of my institute. And by training, I'm not physicist, I'm an electrical engineer. And what I actually do is solve practical problems with simulations. And most of the things I'm going to tell you is actually modeling experiments done by my colleagues, or when I'm lucky and I get a contract, it could be also on demand of the industry. But as you can imagine, we are in the same situation like Argentina. It's not easy to get a contract with industry. So I'm going to tell you something about molecular dynamics, just for the ones who are not very accustomed on what it is and how it works. And then I'm going to tell you about modeling of experiments with AFM. There I have a lot of experience, and I have a lot of colleagues doing AFM, and I really like this technique because it came to application at the same time I got my PhD, which is a long time ago, 20 years ago. And then I'm going to talk about something I did here with Mario, Cindy, and Adriana on intercalation of aluminum fluoride in graphene. And then I'm going to tell you something about where molecular dynamics is crossing or touching the quantum mechanics. So where you can simulate with molecular dynamics to some extent bond breaking, bond creation, and the redistribution of the charges. So which could be interesting for some of us. As I told you, I am part of a relatively big institute, and Basically, the key for my work is the machine which is behind my colleagues, and it is not that new now. It has like 14 years old, but still working, and the colleagues are buying parts and succeeding to make it up and running. Luckily, the computer power didn't increase so much in the meantime, but so 1,000 is was when we bought it. Now it is less, but they try to repair, and it's quite dynamic as with every piece of equipment. So basically, what I'm doing, and what is molecular dynamics? Well, it is a simple approach where you just integrate Newton equations. So basically, it could be done by a high school first. I don't know in the secondary school in Chilean program. So basically, you have Newton's equation and you integrate them with time. During this integration, you are getting position and velocity of each molecule. Of course, if you know position and velocities of each atom or molecule, you know everything, but you also don't know nothing, because you have to translate it in something what is measurable. And that's where fun starts. So you have to translate it in velocity, in pressure, or you can imagine some measure of the system of your own. And then why I consider myself still an engineer is that when you put up a simulation for a problem which comes to your table, is that you have to design this simulation. And of course, you can take a simulation and put everything inside, or very complex model, a lot of defects and all stuff which your colleague coming from experiment tells you that he has. And then when you start, it is not going to work. First, because it is going to be too slow. Then it will crash because the models don't work together very well. And basically, what I after 20 years, I tried most of these models: Reax force field, Eribo, then for water, SPC, embedded atom, that was my PhD, Teresov. So I tried almost all of these models, and I know how they work together, and what are the problems, where they usually crash. And what is very important is computational cost, because you can take a newer model, but usually this newer model require bigger computational cost. On the other hand, if you take older model, you have longer to discuss with reviewer. So, what is actually model, or what is the potential which we use? Basically, you have a single atom, and it is affected by its environment, and this environment could be a neighbors to which it is bonded, if it is a part of the molecule, or a non-bonded atom which could interact with different forces like van der Waals or Coulomb, electrostatic, or dipolar forces. Bonded atoms, they could be bonded by a simple bond, or angle, or dihedral. So basically, if you have 4 atoms, and basically it models hydrocarbons or other covalent bonds. So bonded atoms, so you have this stretching of the bond or compression of the bond. Bending between bonds is angle, and rotation about bonds is dihedral. So basically, you have a potential, and then you make a derivative of this potential. You calculate the force, and now from this force, you calculate integration. And I'm not going to tell more. When I come back in October, I'm going to tell you detail how to implement it in the lamps. It's quite easy. So you don't have to program a lot. You just can choose how you integrate. You can choose integration time step. You can choose many things. It's just a few command lines. It's your choice, and the code is integrated. So what is my field actually is finding simple models for real systems. And I was working for Toyota after my PhD, and I still work a little bit with them. And so basically, it is mostly on lubrication. So finding good lubricants for example for engine there. And now since combustion engines are out of the, they're not very popular anymore. We do fuel cells. So and for that reason, I was very grateful when Mario and his collaborators included me in this small project about batteries, because it gave me one opportunity to come into this field. So I'm just going to tell you about this work with Toyota. So basically, we did a lot last years with ionic liquids. Ionic liquids are basically liquid organic salts. And the good thing is they don't evaporate, so their vapor pressure is very low or even negative. So and the second thing, which is good with them, they're very chemically stable. And the idea was to use, they are already used as additives in the fuels, in the lubricants, for example, for engines. Because if you have this Coulomb interaction, they're going to go very fast to the metal, create a film, and protect metal. And the idea was to explore why they work, to make a model for the company. And for example, the upper curve, you see when you compress a liquid and you take it out, you get like normal force. They can be positive and negative. Basically, as you kick out one layer of ionic liquid after the other, you could also have that the layers are not filled, and then there will be a force which is going to try to approach the two surfaces. And then when you compress further, then you get the maximum where the liquid resists expulsion. And we could also measure coefficient of friction. So this is work from the last year, and many of these liquids are hydrophilic. And in many modern systems, water comes into play, and it's very important, especially with these ionic systems. So I did it last year with US. In US, they have this phosphonium ionic liquids, and there is water. So I changed the amount of water in ionic liquid, and I checked how it distributes inside of it, and compared it with ionic liquid, which is well known, and its own properties modified by presence of the water. So basically, like since last 5 years, I slowly entered into two areas. One is this ionic systems with strong electric or dipolar interactions, and the other is water, because water comes in many systems, and the properties of water are fundamental, because you find it everywhere. But the problem is we have just a few experiments where we can actually measure how the water influence practical system. And one of these experiments is AFM, which has my colleague in France. So basically, this experiment, he can move his cantilever of the AFM in the circle. So usually with AFM you go linearly up and down, but he can move it in the circle. He can measure at the same time normal force and lateral force. Why is it is important? It is important because he doesn't change any velocity or the direction of the velocity during the experiment. So he can have a meters of the path on the same place without changing the conditions. And what he can do is basically he can go with his AFM into the contact, measure the friction in the contact, and then he can raise this AFM out of the contact and show how the meniscus is broken. So basically, in this experiment, you can measure several things. You can measure adhesion force. That's the difference in normal force between going into the contact and out of the contact. So it was adhesion of your probe to the surface. And also he can measure coefficient of friction and also friction at the contact. So which is very important because that's a friction which exists without normal force applied. So this is a little bit more complex friction law than in the textbook. So you have lateral force, which is equal lateral force when there is normal plus force plus this regular friction force which exists. And what is also nice in his experiments is that he can measure at the velocities which are almost on the practical scale, so 1 meter per second. So he compared to regular AFMs, he can go to millimeters per second, which is quite high for AFM. And he can also vary the velocity in a very wide range. And here what you can see is that he obtained for friction of the graphite on the graphite, that adhesion force is not changing with the velocity, which was quite strange. But also when we looked into his experiments, we saw that lateral force is depending so that the friction coefficient is depending linearly on the velocity. And also, so here you can see, I don't know, it's I can show it here. Maybe I should. I should be in the laser. Okay. Yeah, thank you. And then you can see here, this is adhesion force, this is coefficient of friction, it depends on the velocity. And then also what happens is that this in the contact lateral force is depending also on the velocity. So I started to make simulations, and at the when you make a simulation, you start with something. I just placed on the surface water, and then I created the probe, which was about 20 nanometers in the diameter. And then I was looking what happens when I move the substrate, like in experiment under the probe. So first thing is we had a surface which is hydrophobic, because they measured the contact angle, and their HOPG was hydrophobic or weakly hydrophilic. And the idea, the first idea was, is there any water on the hydrophobic surface? And is this water going to stay? So we had a lot of water molecules in the air, but after some times, all this water was agglomerated in form of the droplets. And then when we started to move the probe, the droplets got assembled and created a big droplet under the probe. And when you think hydrophobic surface in the reality, it's not that they are empty of water, but actually the water likes more to stick together than it likes to stick with the surface. So the idea that hydrophobic is surface is dry is not correct. There will be water droplets, just they are going to agglomerate much easier than to spread around this surface. So basically what we realized is that probably the probe as it was moving, it accumulated the water under itself, and then it started to drag this surface, these water droplets as it was moving. So then we made a simpler experiment where we just put a probe, a droplet, a surface with a large amount of water and large amount of, and then we were pulling. And then this probe we attach to the springs, like in the experiment, and we measure the forces on these springs. So, and then, so you see here that there is just a hole that you see that substrate is moving. So substrate is moving. The probe is going up, and the droplet in one moment snaps. And in this process, I can measure lateral force. I can measure normal force acting on the probe. And what is very nice is that I could make a simple model based just on surface tension and the surface energy of the substrate. And I could explain this, how the normal force for different contact angles evolves with normal force evolves with the distance and the deformation of this droplet. So and it was very strange, but then it is also not, because you can apply continuum mechanics for surface tension also already for droplets which are like 5 nanometers large. It was already a long time shown. And the second thing is I could show that also surface and lateral force depends linearly on the contact surface. And for you, this you could say is evident, but actually if you look in the literature, it's not evident. There are like two schools of thought. One school of thought says that the resistance to the movement of the droplet comes from the resistance to the slip. So basically a surface to surface interaction. The other school of thought says that resistance to the lateral motion comes due to the movement of the contact line. And what this result shows is that it is resistance to the slip. The second thing is that from these experiments, I could also measure how lateral force depends on the velocity, and I get that it depends with following exponent. So it's less than linear. And so basically, at this point, I can show you the comparison of what my colleague got in experiment and what I got in simulation. So I got that lateral force depends less than linear on velocity, while my colleague got that it increases much faster with the velocity. And one of the explanation, but of course, I couldn't check it. We couldn't check it. Is that in his case the volume is increasing with the velocity, and because of that he has higher exponent. But of course we couldn't prove it. But there should be some dependence on velocity, which is obtained both in simulation and experiment. And then I would like to show you something what we are working currently on. And that's basically to trying to explore this, how it depends on the velocity. And here you can see a contact angle which is 75 degrees. And then what happens is that first you have accumulation of water under the droplet, but then velocity is high enough that this resistance to slip starts to pull the part of the droplet out of the contact. And basically, the surface tension cannot keep a droplet anymore together. The droplet first grows, but then it is so big that the surface tension cannot keep the water inside, and it is pulled by moving substrate. And then you can see how this process continues in time. So the droplet gets a certain critical value of the volume, and then it's completely drained out by moving substrate. And then we can have even more hydrophilic surface, so contact angle 30, but slower velocity, and you are going to see how the substrate, despite stronger interaction with the water, is not able to keep to take out all water out of the. And just to explain you the colors at the beginning of the simulation. So the rosa were the molecules which were attached with the probe, and the blue were molecules which were detached from the probe. And then you can see also diffusion and how everything mixes together. But this is work in very slow progress, because it's all the time trying to get good experiment and to check it on many substrates and many velocities in order to be sure in what we are claiming. So this is a conclusions for this part of the talk. So the water bridge is created. That's our hypothesis, by accumulation of water, not by condensation, as it is claimed, because condensation is too slow process. Lateral forces depend on contact surface and velocity because of the slip resistance, and we think that all this stuff is very complex behavior of this resistance to the slip, friction, and surface tension. Okay, so now I would like to tell you something what I did with colleagues here in Santa Fe, or more my part, because I really don't understand so much experiment. And so the intercalation is interesting process because it occurs in batteries, but I have colleagues which produce two-dimensional material by liquid exfoliation, and now they are producing two-dimensional self-assembled surfaces with molybdenum disulfide and other materials, which has electronic properties by taking out of liquid these layers. And so it's interesting process, and of course, polar molecules are interesting because there is water, but there is also other polar molecules. So, and the models are similar, and one can learn if one understands one polar molecule, we can understand many others. So basically, this is introduction. So as I understand it, there is these aluminum fluoride molecules which enter under through the holes into HOPG, and then they start to create islands. And so basically, this is my simulation, and you can see what was very interesting what they saw in my simulation is that from between different layers you have aluminum fluoride, and then these molecules created like clusters, but then these clusters came together and they interacted through the layers, and this prevented their motion. And somehow we get like chains of the clusters on different depths. So here, if you have a depth, and then different clusters have different colors, then you see that for example, these ones were above the white ones, and the white ones were above the blue ones, but then there was a red one which was above the blue one. So you had like clusters which were stacked between different layers. And then this is if you look clusters, but then if you look surface, then you would see like two patches, but then also the graphite would be raised and form a line connecting these edges. So you can see here there are like two islands which are not that much pronounced, but there were interaction between these two big islands. So this could indicate formation such three-dimensional structure. And then this was an experiment. So usually if you have like 2 points, you can draw a line through these 2 points. But then if you have 4 points, maybe it's not just random correlation, but there is some interaction under the in deeper layers, which is making these clusters align. And so this is simulation. So compared to experiment, where this process is gradual, so you have molecules entering. What I did in my simulation, I just create a sandwich, and then I in one moment I turn on the simulation, and these molecules start to agglomerate, and they start to create chains. And then in certain moment, they are going to stop to move. Why? Because first, these clusters are far enough. And the second is because they interact close together. And what was very interesting is that basically they were kept together by this electrostatic interaction, but also by a graphite which was deforming and pressing them together. And what is good with the molecular dynamics is that you can create really big systems with many molecules and also a lot of big graphite surface. I mean, bigger than in DFT. And so basically what we claimed and what was the result out of these simulations is that maybe there is this mixed stage model where you could have different number of layers between different polar molecules, not that it is uniformly filled. So this was all more or less classical molecular dynamics, but now this is a molecular dynamics which is going into DFT. So it is work which I did with a colleague from my institute, which is now a professor in Austria, and they're basically creating different devices with carbon materials or two-dimensional materials. And you can see here there is like an electrode, and then they put different layers, and then they put a graphite, and this graphite is functionalized. So they can function. They its edge can be oxidated or fluorinated. If it is fluorinated, it's hydrophobic. It will not attach to water molecules. If it is oxygenated, it attaches water molecules. And then they can prove that it is water which is actually doing the switching. And basically, when they apply electric field, they can cause that there is a hysteresis. So basically, they can have a memory store. So basically, a transistor with memory effect. They apply electric field, and then they can determine different its resistivity. So and basically, for me, I'm not really interested in electronics of this system, but for me it was interesting to assemble a simulation for him, because he asked me, can you calculate me electric field distribution in this system? And I applied this Rex force field model. So basically, Rex force field model is different from regular molecular dynamics models, because it can also determine bonding, and it can also dynamically calculate the torsions, bond breaking. You can even calculate, for example, how hydrocarbon burn and the products of this chemical reaction. But for me, what was interesting is that it can also determine the dynamically charges and calculate Coulomb interaction. So basically, but still it is molecular dynamics, so it's quite efficient. And so I had like a piece of the graphene, which was 20 nanometers by 35 nanometers. I had oxygenated. I put the water molecules on this edge, and then I applied the electric field. And basically, when I apply electric field in this direction, I have water molecules which get polarized. So they start to be along electric field. And then when I start to switch electric field, these water molecules keep the polarization in one direction, and then their electric field is opposing external electric field, and this creates this memory effect of transistor. And then when electric field is strong enough, I could turn off this interaction. So it was all fine. Then I was playing, and then I realized there is a problem with this image. So basically, if there is just one layer of the graphite, when I would turn off electric field and let system a little bit longer in my simulation, these molecules would not stay. So the barrier of them switching the sides and the changing polarization was around room temperature, and they had this transistor effect stable at the room temperature. And then I realized it couldn't be all. So then what I realized is that actually you need to put two graphite layers, because what is happening is that in this case you have the barrier which is around room temperature, but then if you have two layers, then what happens is that you have water molecule which creates a bridge between two layers, and then what is moving is not single molecule, but actually a cluster of water molecules. So in that case, while when you have one water molecule, it has a small energy barrier, but then if you move a whole cluster, then each of these molecules locks other molecules in the state up and down. And that's basically this collective motion of the water molecules creates this stable transistor effect. So and this is the result. So basically this is with the number of layers. And then you have 1, 2, 3, and then you can see here the opening of these hysteresis with the number of molecules, which is above the plane and under the plane. And this is how it evolves with temperature for 2 layers of graphite. Or 2 layers of the graphene. So basically, the hysteresis doesn't close. But this all required really large systems in order to have a good statistics and to avoid, for example, that one edge interacts with the other edge, because there is also this with these strong electric fields. And so basically, then the colleagues had to repeat their experiment and really carefully perform experiments on a single layer device, 2-layer device, 3-layer device, and then this was the result. One monolayer device, B4, 5, 3-layer device, and so it and we are still in review, so we have a lot of trouble to persuade reviewers with this paper. But I really like this work because it helped me to try this React force field model for the first time and try to really push it to the limits, because usually it was used for a few molecules, but this is like you take a model developed for one thing and you apply it for something completely different. Okay. And outlook. So I'm really interested in this capillary water, and why capillary water is interesting is because now with this stupid war, there is a lot of talk about chips and chip production. So and how chips are important. So basically, when they manipulate the masks of the chips, they have to really have a precise positioning, and for this positioning you have to mechanically move these masks. Despite all quantum mechanics and advanced optics, you have to move a mask mechanically, and for this you need really to have a good control of contact, and there is always water which is entering. So this is why we really have to control capillary water. But also, I mean, capillary water is controlled on the screens, because your finger is hydrophobic and you touch a screen, and many surfaces are defined, are designed to have this water mediated interaction. Then dry lubricants like molybdenum disulfide are called dry, but actually they fail if they are not in presence of the water. So, for example, if they try to lubricate something in space with molybdenum disulfide, it is not going to work. Or on Arctic, because molecules get trapped into 2D materials. So that was also a question by a colleague. So basically they have AFM and they compress really hard materials. And then they ask us, okay, is there a water molecule trapped in this contact? And we showed that there are water molecules trapped in the contact. And then, of course, interactions of molecules with 2D material edges is also how they enter into different materials. And this is actually the photo of Zemun. So, and the Belgrade is on the other side. And we are also on the edge of big river. So it's Danube, which is about 1 kilometer here. And actually this is island in the middle of the city, and the other river is coming in. So yeah, we have a lot of rivers, and my daughter does kayak. So yes. Okay, thank you very much.
Well, another similarity with Santa Fe.
Exactly.
Okay. We have questions? Yes.
Okay. Nice talk. I'm wondering if you check or recheck your parameters using quantum mechanics, because my understanding is that you are using the standard parameters in your simulations. Are you checking with more sophisticated method, validating the parameters?
Well, in case of aluminum fluoride, Cindy checked basically because there was no parameter for interaction of aluminum fluoride with a graphite. So there we adjusted parameters to fit the DFT. In case of Rex force field, there is a group by Goddard which develops these parameters for molecular dynamics systematically. So I don't check there. Or, for example, for these classical applications with friction, we don't check their parameters. Now we have fuel cells, and there is ionized water, hydronium, and there we are just now working on checking the parameters which we are using. So it depends. Sometimes we don't have to, especially if there is some mechanical deformation. It doesn't, I mean, the system is so dirty that if you go to improve parameters, you're not going to get something. But on the other hand, if it is proton transport, then yes, we double check parameters.
Miranda?
Thank you. Hola, hola. Hola, hola. Hola, hola, hola.
Well, they could move if there is a hole in the HOPG, but we didn't simulate the holes, and probably there is not many holes in the bulk of HOPG. It's almost perfect crystal. No. It's you need really high energy, even for hydrogen, to penetrate the graphite lattice.
All defects you have in the surface, not only edges. If there are another defects, you will have intercalation through them.
Gustavo, I have forgotten Gustavo.
Hi, Igor. How are you? Nice, very nice talk. Igor, I wonder if you tried to simulate some other tribological interesting surfaces, like for example the tribological properties of boric acid phidons, which is in that case very dependent on the hydration. I mean the the humidity, and its tribological properties are very dependent on that.
I didn't try boric acid, but it would be interesting. I could try it. I mean, but it is acid, so it has to give somewhere. It will probably ionize something. So
yeah, maybe because I was reading it very interesting. I will share with you later about tribological properties, and they discussed materials such as graphite, and you already mentioned the molybdenum disulfide, but they also did experiments on these tribological properties of these boric acid films, and even boron nitride, which forms more compact structures and are quite interesting.
Yeah, the boron nitride has similar structure like a graphite, but boric acid, it was on silica or?
It was on silica. I mean, I think.
Yeah, because they do a lot on this tribochemistry on silica, because even water interacts with silica and creates a film. So it's a whole other topic about this tribochemistry, which is quite interesting now. But I didn't do much about that. So
nice. Okay, thank you very much.
Hi, very nice talk. No, I would like to know a detail about the interaction in the last part of your talk when you talk about the molecule, the water molecule with the edge of the graphene. Oxidated graphene. Okay. And do you have graphite or a lot of layer of graphene? And how is the final or the edges or the termination of your layers is going to affect the interaction of the water? I think.
Yeah. Okay. I didn't want to go in great detail there, but it's actually a very good question. Maybe this is a good pictures to start. Okay, so basically, yes, it was several layers of graphene, not graphite, and then it was terminated with oxygen in my simulation, and then basically what happens is that you have a redistribution of the charges, so oxygen is negative, and then basically you will have a positive carbon and then negative carbon. I see like a charge transfer towards the edge, and then you have hydrogens which are positives, which get connected very strongly with hydrogen bonds to these oxygens at the oxygen terminated the graphite. And then what happens is you can see always that hydrogens are pointing towards the oxygens. So basically that creates this whole, but the charges are calculated dynamically. So when the environment changes, the charge of the local charges of the atoms, they change. Okay, and this model also, but we didn't see it can break the bond. So basically, it could also break the water bond, and the hydrogen could leave the water. But I mean, the temperatures were quite low, and this wasn't happening. But what I saw is redistribution of the charges. Yes, the oxygen is terminating the graphite. That's actually the key, because if it would be